Okay, all right. So this is the third lecture in the series of lectures on the social network analysis. And today we're going to talk about mathematical models of networks. All right, so why do we want to talk about models? Well, the reason is that the models are usually a simplification of reality. And, just reality is too complicated, and sometimes we really don't understand what causes what, and sort of if we want to look for like root causes of different things, it's very, very hard to do. So instead, what we're trying to do is we're trying to model the reality, make a model simpler than reality, and that's actually the goal for a model. Sometimes you want to have a model that exactly reproduces reality. Sometimes you want it to be approximate reproduction of reality, right? But at the same time, you want to have the model to be interpretable, right? So, and then what you can do is, you can take this model, look at the parameters of the model, see how it affects the behavior, and then make certain assumptions about, about our world, about the reality, all right? And so that's the whole point of modeling and building a model that are simpler than reality, right? So we do understand that what we're doing is not perfect, but we're trying to balance on one hand sort of reproductivity of reality, reproduction of reality. On the other hand, we're trying to have something that we can certain control on, and some parameters that can help us understand the behavior of the model. So in this sense, what we're talking about here is not a black box model. It's a model that has explanatory power. Moreover, the models we're going to look at today we'll talk about generative models. So these are the models that allows you to generate networks, right? So pretty much the idea is we take the model, there's 7 parameters in the model. We use them to generate a network. Then we compare this network with reality and see, okay, if whatever we generated looks like a real network or not, and which features of the network that we generated matches the features of the real network. And then we can sort of adjust model and see what happens. And again, different models will produce different features of reality of real networks better than others. And sort of the goal is to actually use this model to understand what happens in the real life. Okay? So, and in fact, what I just described you is sort of general principle. It's a general principle for model building, not necessarily networks. But today we're going to talk about models for networks. So we're going to talk about 3 different classes of models, and these models, they all they started the network theory. So today you will find many more models than these 3, and most of those are one or sort of another type of extension of these models, or maybe combination of these models. So these are 3 basic fundamental models that exist for networks. And so the first one is what's called random graph model, and that model goes back to goes back in time to 50s and 60s, and it comes from famous mathematician Paul Erdős. The second model is preferential attachment model. That model, or it's also called Barabasi-Albert model, that model has been created like around the year 2000 in response to the increased interest in network analysis and the scientific efforts to understand what networks are. And in fact, by the way, if you're looking at the book, I recommended for the course, Barabasi is one of the authors of this book, right? And Albert, I think he's a graduate student or postdoc, I don't remember. And the third model is a small world model. This is also a model that has been created in around the year 2000, again, in response to understanding of what real networks look like. And the first model, this one is again 1950s. This is like what sort of mathematical curiosity for great mathematicians into new objects, which are random graphs. And until the year 2000, pretty much until this time, people thought, those who thought about networks like sociologists, et cetera, those who were mathematically inclined, they actually thought that the real world networks can be described by this random graph models. And what we're going to see now is that the random graph do explain certain properties of real world networks, but not all of them. So that's really more of mathematical abstraction. But again, it's an interesting model, and it helps us to understand certain type of processes that happens in the network. So just to remind you from the previous lectures, there are several empirical network features that we would like to be able to reproduce through the models. So first of all, it's a node degree distribution, or power law, or in other words, heavy tail distribution, which means we have some nodes with a very, very high node degree, and that's like hubs. These are very, very connected nodes, very, very connected people, celebrities in Twitterverse, right? And the majority have very low degree. So power law degree distribution. Second, the property of a small world, or sort of 6 degrees of separation in between people, right? The small graph diameter. The third property in the networks we see is this large clustering coefficient, or the fact that in social networks there are lots and lots of triangles. So friends of your friends know each other quite often. That property. And final property, it's kind of a little bit weaker property, but it's also being always observed in these networks, is the fact that they do have gigantic connected components. So there is usually within the network, there is a big component where all the nodes reachable from each other, and then there is some sort of leftovers, maybe 20% of the network are separate, right? They might be like also larger components, but this one like significantly dominates. All right. Okay, any questions so far? No. Probably not, right? Okay, so let's jump in. So first of all, random graph model. Now, this model, actually, it's a very interesting, mathematically interesting model. The really interesting part about it is that, again, it was presented by mathematicians, and so they actually investigated lots and lots and lots of properties for this graph, and actually proved lots of theorems. And if you're interested, if you're into this, I would strongly recommend to read original papers. They're very precise and very good. Now, for us, this is just sort of the big idea of this model. Imagine that you're having a party, right? And you invited, 10 people that do not know each other, right? And of course, when they're all in your apartment, at your party, they start talking, right? And imagine that there is a certain probability that 2 random people who do not know each other, will start talking. And that's what usually happens, right? One person bumps into another, then there's a conversation. So the question is, all right, let's say, you have 10 people in your group. So in your party, then, so how many possible total number of connections that could happen? Well, each person can talk with each person. So it is like 100, I'm sorry, 10 people, right? So it's 10 squared, which is 100, but we don't want to double count. So it's going to be a little bit less, right? You divide by 2. So, and you don't want people to talk to themselves. So it is actually 10 times 9 divided by 2. That's how many total number of pairs you can form if you have, this number of guests, and they sort of randomly start pairing up. Okay, so if they do that, if that happens, you realize, that for some people, some people will just talk with another person, but then you might actually see the situation when, somebody actually in the middle of conversation with 2 people, right? Just again, imagine the party. And so the question is, after some time with this kind of situation, first of all, how many conversations you will have going on, right? So, and by conversations, I mean like literally how many edges there will be in that, friendship or conversational graph. It's one question, right? And the other question is, all right, well, how many people will have who will be talking only to one person? How many people will be talking to 2 people? How many people will be talking to 3 people, et cetera, et cetera, et cetera, right? So these are very simple questions, and there are, within this very well-defined model, there are very simple answers for that. So the model itself is defined through number of by given, I'm sorry, is defined by given to you by number of nodes or number of people, and the probability that each pair of those nodes is connected. So if the probability that every pair is connected is equal to 1, it is fully connected graph, everybody is connected to everybody. If probability is equal to 0, nobody's connected to nobody. And if it is somewhere in between, for any two nodes in the graph, there is a non-zero probability, right? There is this probability P that they're connected, okay? So the first question is, if that's the case, on average, how many connections this graph would have, right? How many edges will be in this graph? And to compute that average, what we do is we'll calculate the total possible number of connections. And again, if you have n nodes, then for every node, there is n minus 1 other nodes it can connect to, right? So the possible total number of combinations is n times n minus 1. And we don't want to double count because we say this guy is connected to this guy. Well, this guy is already connected to this then. So that's why we divide by 2. So that's a possible total number of connections. And then in order to calculate average or expected value, we just need to multiply by the probability of those connections. And so that's where you get this m. So if p is equal to 0, average number of connections in this case is 0. If p is equal to 1, it's 1. I'm sorry, if p is equal to 1, it's total, it's maximum number. And in between, whatever we get. And the thing is, why it's average? Well, because looking at the different parties, or even like repeating this sort of exercise for your own party many times, you will be getting little bit different numbers. And that's why it's average. It's average over multiple implementation of this graph. Now, you can also calculate, average node degree on average number of people a person would be talking to, at your party, and you can calculate it as, of course, just adding up node degrees of every person and 1 over n, and we can approximate it. We looked at this formula last time as twice the number of edges divided by the number of nodes. That's that's what it's going to be equal to. And so I put in the value from the top. I will get p times n minus 1 or p times n. So average node degree is a probability of connections time number of nodes. So if there are 10 people and the probability of discussion, of meeting, forming an edge is 0.1, then average node degree will be 1, right? If you have 10 people and the probability of forming an edge, is 20%, then average will be 2, etc. So and this is sort of the key factors. Now we can also talk about the graph density. Now graph density is the ratio of the edges that are present in the graph divided by the maximum possible number of edges, right? And again, maximum possible number of edges is when everybody is connected to everybody. And so this ratio is called graph density. And if we plug in numbers and compute it, we'll see that it is actually equal to this probability of two nodes being connected. So graph density and the probability of two nodes being connected is the same thing within this model. And that again means, when probability of any node, any pair of node being connected is 0, well, density is 0, no edges in the graph. If it is equal to 1, everybody is connected, graph density is equal to 1. And, real life's usually in between. Make sense? Okay. So here's the picture. This is a random graph I generated following these rules, right? So I took all the nodes, however many nodes we have here, and for every pair of nodes, I flipped a coin. So I selected, let's say, select this node and this node, flip a coin, and see, okay, if we're going to connect it or not, right? And there is certain probability that they're going to be connected. Let's say, if if I say like probability is 0.5, you know, I actually flip a coin and I'll say, okay, if it fails, you know, we connect. If it not fail, we do not connect. And okay, what happens is those two nodes are not connected. Then I pick up this pair, say, or you know, I pick up, I don't know, this node and this node, flip a coin, and you know, the coin comes down and it's connect, and it says, okay, it's connected, so I connect them. And so I do this with all the possible pairs of nodes, and that's how I build this graph, right? So what you see on the right is when we build this graph, we can actually, the same way as we did in the previous lecture, we can go and measure and calculate how many nodes of degree 1 we have in this graph, how many nodes of degree 2 we have in this graph, how many nodes of degree 3 we have in this graph, etc. And build a histogram or distribution of node degrees. And that's what you see here on the right. This is a distribution of node degrees. And what it says is that majority of nodes in this graph is actually, they have degree, you know, around 5. And we do have some nodes with degree less than 5, right? With degree 4 and 3 and 2. And we have nodes with a higher degree. We have a node with degree 10. We even have a node with degree 15. And if I smooth it out, that's the distribution I get. Well, this function, within this particular model, we can actually calculate this function. We can calculate it precisely. And that's called a Poisson distribution. And it has the following formula. So probability that a node degree is equal to k is given to you by this ratio, where it's lambda to power k divided by k factorial. And remember, k is a node degree, so it's an integer, so we can do factorials. So it's lambda to power k, k factorial, and it's e minus lambda normalization. So what's that parameter lambda? Well, the parameter lambda is p times n, so probability of nodes being connected times number of nodes in the graph, or average node degree. So what we can do is, you know, in this case, you know, like average node degree is 5, right? And so this graph is centered around the average node degree. And so what you're seeing here is that, again, there is an average node degree. There are some nodes with degree less. There are some nodes with degree more than that. But overall, you know, the majority of the nodes have a degree 5. So in some sense, this graph has a scale, and the scale is that, you know, nodes do have a, you know, majority of the nodes, right, have a degree 5. Now, this is very different from what we described as network, as social network as Facebook, or what we see on the web, right? Over there, we're saying there are several nodes that have very, very high degrees, and the majority of the nodes have low degrees. So this model, though it is very sort of intuitively nice and clean, it actually does not produce the networks that have the distribution that we see in real life. Okay, so this is a nice model, nice understanding, but the distribution it gets it wrong. Okay. Now, but why are we still studying this model? Well, because it actually gets some other properties right, correctly predicts some other properties. Plus, it's actually a very nice model. You know, there are nice parameters. You can tune them. You can twist them and see how it affects the result. And it is a very, very clean model in the sense that, you know, it's solvable all the way through, right? So it's sort of mathematically provable things. So what's interesting about this model? Well, if you think about this graph as a function of the probability that connects to nodes, right? So as I said, there are sort of two parts in this, right? There is a situation when p is equal to 0, and that means, you know, you have an empty graph, nodes are not connected. And then this is p equal to 0. And then there is p equal to 1 when every node is connected to every other node. So it's fully connected. And when we change things from 0 to 1 when we increase this probability. Things happening. And it was observed that somewhere in the middle, all of a sudden, we start getting a situation when you can almost reach any node from any node, right? But only maybe, you know, using one particular route. So again, imagine on the left, you have completely disconnected. On the right, it's completely connected. So if you want to go from this node, for example, to this node, you know, there is always a direct way to do it, right? So everybody can get in one step from every node to every other node. But somewhere in between, there is a situation. Oh, and by the way, so this is the shortest path, but there's also many other paths you can get from one node to another, right? You can get through very many ways. Now, there is a situation, there is a sort of intermediate step when you go from left to right, when there might be just only one way to get from one node to another. So there is still a connectivity. Nodes will get connected, but there's only just one way of getting from any node to any node, right? So it's sort of a tree kind of structure. So we go from nothing to this sort of, you know, connectivity, or light connectivity, to completely connected. And what's interesting, it's mathematically possible to actually determine the moment when the graph goes from sort of separate disconnected pieces to connected piece. And that point is actually called phase transition. It's the same story as, you know, if you remember a little bit of physics, when you go from cold water to ice, right? When there is a particular point, and it corresponds to 0 temperature, right? When water becomes ice, like, so it's getting colder, 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 nothing happens. And then, oops, you got ice, right? So here, the same story. You have a bunch of nodes that are disconnected, and then you increase density of the edges, or probability of nodes being connected, and all of a sudden, there is a connected component. So, and again, being a very nice mathematical model, it actually can be calculated and computed precisely. What I'm showing here on the left is exactly this simulation. Here, I build a random graph with probability of probability of edges being less than this critical probability. Now, the second picture is this probability being around this critical probability, and you start seeing this, you know, big component appearing. Over here, there are just small pieces floating. Here we're seeing big component, and if I keep increasing slightly, I will get to the situation when all of them will get connected. And if I keep going, and that's probably P greater, much greater than C, I will get a situation when majority of them connected, and there are sort of multiple routes to get from one to another, right? So first of all, to make this model, to simulate this, of course, as always, there is a nice function within iGraph that allows you to simulate this. And what we observe here, this is a phase transition, when all of a sudden, you know, big chunk of nodes getting connected. So does it make sense what's happening here? Sort of?
Yeah. Really?
Okay. All right. Okay. So one can actually show, and that's sort of what's being shown and mathematically proven, that the critical point is when Pn is equal to 1. P is a density of the node. P is a probability that the nodes are connected. N is the number of nodes, and it's equal to 1. Now, there is actually very, very simple. If you look back onto the slides, you also see that this value is equal to average node degree. And so what this really says, we get phase transition where on average, every node gets at least one connection. So when on average, every node gets more than one connection, then when they start connecting into this big, gigantic connected component. And there is a sort of mathematical way to prove this. I'm not going to go into this, but again, you can look it up if interested. So that's sort of the big part of this story. And there are, a lot of details into this, how those things form, and how when this P is less than critical, or average node degree is less than 1, we have only small components. When the average node degree is equal to almost getting to 1, we're getting a pretty large connected component that contains like 2/3 of all the nodes. And when it's getting greater, it absorbs all the nodes. Now, one caveat here: all this true when it's mathematically correct statement when we consider limit of number of nodes going to infinity. In any modeling or simulation you do, you cannot get n going to infinity. It will be some finite number. And so you will see these properties, but they might not be like as crisp as described here. You will see transitions maybe not exactly at 1, but just a little bit above 1. You may not see all the nodes being connected, but majority of the nodes, etc., etc. But at n goes to infinity, this is mathematical fact, mathematically proven fact. And with smaller n's, this is something we can actually observe in the models, right? The way I showed you on this picture. So what I can do is I can calculate, actually, let me go back here. What I can do is I can calculate the fraction of the nodes that belong to this gigantic connected component, right? So here, all of them, and the fraction will be 1. Here, the fraction close to 0. Well, and in the middle, there is something happens. And so for those pictures, I actually did compute that fraction. It's again number of nodes that belong to this gigantic connected component as a function of, in this case, I showed it as function of p times n, not just p, but p times n, on average node degree. And so what it shows you, if node degree is less than 1 on average node degree, then a fraction of connected nodes is close to 0, like they're all sort of disconnected there. But as soon as I cross this limit threshold where you get at least 1 connection per node, and then more than 1 connection per node on average, we start getting more and more nodes getting connected, and it's actually very, very quickly saturates. So in this particular model, in the one that I showed you in particular simulation, when you get to on average 4 nodes for connections, we get all the nodes in the one component. Now, the bigger the graph, the more the sharper this transition will be happening. What you're going to observe in practice, if you try to do it, it will be the blue curve that I've just shown you. And so this is a really cool property. So you have this control parameter that allows you to take the graph, disconnect it, and make it into nicely connected, and see through this phase transition, through the sort of freezing point, right? So that's the sort of the key property of this graph, is this existence of gigantic connected component. Now, we can actually calculate clustering coefficient in here, and it's very, very easy to compute, because if you remember, clustering coefficient is a probability that, if you're connected to 2 nodes, right, you have 2 friends, clustering coefficient is just the probability that those 2 friends are connected. Well, in this particular setting, within this model, the probability that 2 nodes are connected does not depend on whether their friends are connected, and it's just equal to p. Or we can actually just calculate it the way the definition gives us: number of links between nearest neighbors and maximum number of possible links between them. And plugging in numbers, you will see that clustering coefficient here is proportional to p. But the key point, the key message is that within this model, the probability that 2 nodes connected does not depend on if their friends connected. So this neighborhood connectivity, that triangulation, is not part of this model, right? The fact that those 2 guys know you does not change the probability that they know each other, which we understand is wrong in real life, right? But this is this model, right? So for this model, the clustering coefficient is just equal to the probability that the nodes are connected. And obviously, if you get for a very large graph and you fix, for example, node degrees, this probability will go to 0. So random graph does not have a lot of triangles in it, unless node degrees are very high. Now, the diameter of the graph, that is the computations we already also done on, I think, on the first lecture. As I mentioned, if we look, and again, this computations right now we're going to show you, it works around, this critical point, right, where nodes just got connected and there's just one pathway from, every node to every other node, so they form a tree. Now, if they form a tree, then it's very easy to calculate diameter. It's going to be harder if you get sort of additional connections when things start getting more and more connected. Then diameter is hard to compute. But around critical point, when things are connected only as a tree, it's easy to do, right? And the way to do it is to say, okay, well, if every node has k average, on average has k neighbors, then after one step, the node has k connections average. After 2 steps, it has k squared. After 3 steps, it has k cubed connections, etc. Right? The person has 10 friends. Each of his friends have 10 friends. So it's 2 steps away from you is 100 friends. 3 steps away, 1,000 friends, etc. Just again, absolutely trivial model, but it works around critical point because that's when graph just becoming a tree. And so if that's the case, then we can say k to the power d is proportional to the total number of nodes in the graph, and so we can actually estimate the diameter, right, by taking a logarithm from left and right side of this equation. And so what you see is that the diameter is proportional to the logarithm of the number of nodes, and that is a small world property, right? So the number of nodes growth. You have 10 nodes. Let's say it's it's logarithm based 10. You have 10 nodes. Diameter is equal to 1. You have 100 nodes is equal to 2, etc. So it grows as a logarithm of number of nodes, which is very, very slow growth, and that's sort of what small world is about. Even if you have a large graph, say 10 to the third nodes, which is large already, 1,000 nodes. Average node degree, average path distance will be here around 3, right? And you have a million graph, it will be 6. So in this sense, the model actually does a good job predicting things compared to the real life. So summing up for our R-near random graph model, node degree distribution is Poisson, which is not power law. It's not what what we want, what we see in real life. Average path, so this is minus. Average path length is right. It's logarithm of the number of nodes. Clustering coefficient is not good. It's small. There is no triangles. But, and by whatever reason I didn't write it here, there is also this gigantic connected component, right? The fact that this model predicts the existence of gigantic connected component, and that's plus. Plus means that exists in the real world. So as we discussed at the beginning, this is a model. It simplifies what the real world looks like, and there are certain properties that it predicts well. Now again, the importance of this model is it's the first model. It's actually a mathematically precise model, so it's things are provable through it, and it does predict certain things. I pause here for a second. Any questions? I know we're going fast, but we're sort of short on time.
No questions.
No questions. Just a sec. Okay. So next model I'm going to talk about. Yes. Okay.
Do you define first what is the nature of the information that they're talking about, or they're just meeting? What is the nature of the appearance of the connection between
Okay,
them?
yeah. So this is it's a good question. Now the model is very abstract in the sense, I used this party kind of meeting as a intuitive introduction to it. In general, the model is completely abstract. It says we have nodes, and there is a probability that the two nodes are connected, and that's what's in there. Now, then you can think of, if it is, type of a party situation, then it's a probability that people meet. If it is biological network, it's a probability that those two molecules will interact, right, et cetera, et cetera, et cetera. So it's completely abstract from the mechanism behind this probability of connecting. Does it make sense?
Yeah, but in other the probability, it's also calculate the number of possibility of connection between them, or what is the most close to each other, you connect them. That's it.
Yeah, you can do that if you think about geometric number. I'm sorry, geometric network. But typically, again, the way it was presented in our original paper is you have n nodes, right? Actually, I have it here. Right? You have a bunch of nodes, and what you do is you randomly pick up a pair, pick up this node, for example, and this node. Flip a coin. Let's say probability of connection is 1/2, right? And then you play a fair coin. Flip a coin. Let's say if it's tails, you connect them. Then you pick up another pair of nodes randomly. Flip a coin. It tails now. You do not connect them. Then you pick up. You again can pick up randomly this guy and this guy. Flip a coin. It's tails or heads. You connect them. Then you randomly pick up, and it happens that it's again this guy, and then you randomly picked up, and it happens to be this guy. You flip a coin, it's again heads, and they're connected, and you connect them. And so you go through all the possible pairs and connect them with a certain probability until you run through all the possibilities. Make sense?
Yeah.
Okay, good. So let's move on onto the second model. Now, there is something about this model, the one I just described, that that doesn't sound right. In some sense, in this model, what we use is a very strong assumption that the number of nodes doesn't change with time. So it's a static model, right? So it is like, here is our 10 guests, they already in there, and then we're just making them connect. So there's no dynamics. At the same time, we know that, let's say, if you look at the Facebook, there are few people appeared there at first, then there are more people connecting, then there are more people, new people coming in, et cetera, et cetera. So you get more and more people joining, more and more nodes appear. Even if I think about this party problem, you got first guest coming in, and then the second guest, and then the third guest, and then maybe a couple more guests. So there's always sort of time evolution. That's one part of the story. Another part of the story, think about, when you go and again, let's say you don't know anybody, you're at the party, you walk in. What's most likely? Are you going to strike conversation with just with a person that just lonely there, or would you rather join a group talking to about something? What do you think, guys?
Someone alone, I think.
Okay, well, I would actually join a group. It's easier, but that's sort of difference in opinion. Now, another sort of mental experiment, joining social network, and then you see somebody, like, say, for example, invites you to connect. You're going to look at number of friends he has, right? Probably. And if that person doesn't have any friends, would you want to connect to that person?
It depends.
It depends, but most likely no, right? So nobody likes losers. If somebody there and he doesn't have friends, well, yeah.
Don't talk with me in parties.
Well, anyway, again, this is sort of mental. I sort of, again, it's a sort of something for you to imagine, right? To remember, to reflect on. But the point is the following: the original model, the random graph model, assumes the equal probability of connections between any nodes. And what I'm saying is, well, you know, when you come in, or when the node joins the network, it might have different probability connecting to different nodes. I don't know, think about attractiveness on a profile, okay? I mean, it does affect the probability that somebody connects and sends a friend's request. Anyway, again, from this sort of, you know, you can think about like millions of different kind of like life stories, how and why this works, but it was formalized in a mathematically precise way by Barbash and Albert in their what's called dynamical growth model. So the idea, sorry, the idea is the following. At moment zero, at the very beginning, we start with just a few nodes, okay? Just a few nodes, and 0 nodes. Let me try to get different color. Let's say we have a few nodes. And, you know, even 2 of them might be connected. Again, think about a party or social network, you know, 2 people talking, this third person is standing there. And on every step, on every time step, like say clock is ticking, like every 5 minutes somebody comes in. And this person has to join one of the groups. Like he has to start talking to somebody. Now, let's assume, and let's right now, if we're gonna go with example of people talking in the room, he has one connection, right? So he can join one conversation. And the probability of the conversation he's gonna join is proportional to, so he will join that person who has more happening for that person right now, who has more connection at that moment. So if this guy is coming in, and he can join any of those 3 nodes, he will join nodes 1 or 2 with a higher probability that he will connect to node 3. All right? So let's say he connects with node 1. Then there is another node coming in. This node, again, will have an option to connect to node 1, 2, 3, or 4. And his probability connecting to them, again, will depend on already how many connections those nodes have, right? And so with the highest probability, it will connect to node 1. Well, then we can get some other node coming in. And again, it can connect to one of the nodes. It has the highest probability connecting to node 1, but it's a probabilistic, so it might as well, you know, connect to a little bit to somebody with less connections, but still, you know, connections, and it will connect to node 4, and so on and so forth. Okay, so new nodes come in, connects to existing nodes. What I just showed you was an example with new node coming and joining only one node. But we can also imagine a situation when a new node comes in, and now think about, you know, maybe a social network story or something else, and it has like, he can do 2 connections, right? So, you know, like in social network, you can send, I don't know if Facebook restricts now, but it used to restrict how many friend requests you can actually have simultaneously out, right? And so let's say you have, you know, you have only 2 requests you can send out. All right, so the new node comes in and connects to 2 nodes. Then yet another new node comes in. Well, it actually has a higher probability to connecting to these 2 nodes than anybody else. Then there is another node comes in, and let's say it has, you know, 2 nodes it can connect to, and let's say it selects this one and this one. And so the graph keeps growing. So there are 2 things. On every time step, we get a new node coming in, and the new node brings some number of edges, M0. And with these edges, it can connect to already existing nodes in the graph. And the probability of connecting to the node with degree k is proportional to that node degree. So that's sort of this idea of money coming to money. You know, we don't like losers. The more friends you have, the high probability somebody will connect you and make you a friend. All right? You can think this about, like, I talk about this kind of unfair advantage, you know, life is fair, it's not fair, blah, whatever, but that's sort of the model. Okay. So this is a model that the guys proposed in 1999, and then they started investigating this model. So first of all, again, I actually walked through this a second ago, but for you guys to understand a little bit better, this is a sequence of the steps, right? So you have some nodes that just exist, then there's a new node comes in, and in particular case here, this new node comes with 2 edges, right? And it gets connected to some nodes. And when it gets connected, those node degrees increase. And in this slide, what they show in these images, that the higher the node degree, the bigger the circle of the node, right? So that guy could connect it. Then there is yet another one coming in and connects to these guys. Their node degrees are higher, and then a new one, and the new one, and the new one, and the new one. And this dynamics is really, it really corresponds to this idea that rich gets richer, right? So whoever was the first in the game and got some, some money, money flows to money, friends goes to friends, he has this advantage of the first comer. And so the node degrees, the degrees of the nodes that were starting grow, they'll keep growing. And eventually they'll be the largest nodes in the graph. What's interesting in this model compared to previous model of random graph model, nodes here will get disproportionately large. So some nodes will be like actually really large, and others who are late to the game will remain poor. Want a good example? Think about Russia 90s to 2000, right? Лихие 90-е. Well, that's your story. Whoever grabbed money, yeah, and everybody else, yeah. So that is a sort of this is a sort of self-enforcing model where riches gets richer, money goes to money. Preferential attachment. I think this is a very, very good term, right? Preferential attachment. So that's the model. This is just an example for that particular model. Let's say people start with 3 nodes, 3 friends. This is a time, and this is how things grow, right? This is how that's how node degrees or number of friends growing for the person who first joined it, right? Who the earliest one. This is how many friends will get the second one as a function of time, right? This is again the third person joined later. So this person joined, let's say at moment 10 minutes in the party, right? This is at 20, this is at 30, and this is how many friends he gets. And what this graph sadly shows that, you take any time slice, the person who joined the first will have, more friends than you are, okay? So this, again, first mover advantage, very, very clear. Does this reproduce reality 100% correctly? No, it's a model. But you realize if, our real life has this preferential attachment mechanism, that the direction it pushes things towards. Now, this is yet another picture. What I done here, I simulated a graph where when a new node comes in, it has only one connection, right? It can only connect with one node that already present, all right? So every new node has degree 1. And what I also did, I left here the numbering that corresponds to the sequence when node came in. So there's the first node, there's a second, third, et cetera, et cetera. And just take a look. Node number 1, doing pretty good, right? So after we build a graph of 100 nodes, it has a pretty large degree. Node number 2, well, again, it's random process, so it doesn't guarantee you that the first one will always have more friends than second, and more friends than third, than more than friends than fourth. It's a random process. So, but on average, yes, it will. And so this is node number 1, number 2. Number 3, by whatever reason, didn't do so well. I can't even see number 3. Yeah, it's right here. Somehow it ended up only with 2 connections, while all of his peers he started with got much more, right? This is node 5, etc. And then if you look at the latecomers, they're all on the sort of on the periphery of the story, right? Like in the suburbs. So that's what it looks like, the model. Now, of course, you don't always come in with 1 connection. You can come in with 2 connection, or not can come in with 3 connection, and that sort of makes the graph much, much denser. Is it clear how those graphs, how this graph's created? Okay. So the interesting part, and the reason why I'm talking about it, is that this mechanism of reach gets richer, or this preferential attachment mechanism, actually leads to the power law degree distribution. So you can actually calculate that the probability that the node has degree equal to k in this model is proportional to 1 over k cubed. So probability of the node to have degree k is 1 over k cubed. And that is what we observe in very many real networks. So it actually says that, if you know degree is low, the probability of having that load of that degree is very high. And if your degree is high, the probability of having a high node degree is very low. And so that's this curve. For comparison, I'm putting here also a curve, the distribution curve given by Poisson distribution, which is a random network that tells you, okay, on average, everybody has, X friends, and there are people who has, less, and there are people who has more. Versus the Barabasi-Albert model that tells you that majority of the people have very little node degrees, right? This is where the majority of the people live. That's the highest probability, or the most people have very few connections. But there are some people who have a very high connectivity. And so that's the difference, preferential attachment versus random graph. And if you actually look at this, I wanted to generate two graphs that have the same number of nodes and the same on average number of edges. So average node degree is the same. But look how different, the connections distributed. To emphasize how the node degree of every node, I showed it by the different size of the node, right? By using the size. And you realize, can you tell me, by looking at this and just listening through all my explanations, which of these are, which picture corresponds to random and which picture corresponds to Barabasi-Albert preferential attachment? So this is Barabasi-Albert?
No.
Oh, okay, other way around. Yep. So this is, this is random, and this is Barabasi-Albert preferential attachment, or PA preferential attachment. And it's actually, clearly visible, the difference, right? It's again the same story, if you have finite resources, how resources being distributed? Where are they more or less evenly, randomly distributed among people? Or if you get, if the majority of resources will go to just a few people and they will just grow huge, right? And then the rest of the country remains, well, the way it remains. So that's the difference. And that's why, by looking at this and sort of comparing to real life, people realize that, well, man, you know what? This does look like what we see in real life. So this model does have, value in it. Okay?
No.
All right. So this is an example. Again, I ran the model, ran the simulation. And by the way, you guys can do the same. And I strongly recommend you when you're learning these things, unless, I think we probably put it into the homework. But even if we didn't, do it, for yourself. You can. It's very easy. You can run this Barabasi-Albert model for different number of edges that any node brings into the model. Let's say this one node brings in just one edge, right? This node, this situation, two edges. This situation, and your node comes in with 3 edges, and you will see after the same number of steps, how different they are. But what remains in common is that the distribution of node degree will have this shape, this power law shape. Oh, and by the way, as we talked previously, in logarithmic coordinates, that's going to be a straight line. So, preferential attachment model, it gives us node degree distribution as a power law. We didn't do it, but you can calculate that average path length is logarithmically distributed. Clustering coefficients still kind of, nah, not good. So no degree distribution plus, average path length plus, clustering coefficient minus. It does not predict gigantic connected component, unfortunately. So now you notice this model actually reproduces well sort of other things, but it's just a different model. Any questions? Okay, good. Then there is this last model. I'm gonna go through it. Yeah.
This model have not like integer 2, 3, but something like between like 2.5.
So what happens is, you know, the way the model organized, you always have to connect to some number of nodes. But what you can do is, instead of probability being proportional to naught degree, you can actually put any function you want in there, and that kind of, you know, allows you to twist the model. So you're still coming in with this fixed number of degrees because, you know, you need to connect us to other nodes. It's an integer, right? How many edges you bring in, but the probability can be can be calculated different, and so on average, every node will be getting different number of degrees from incoming node. Does it make sense?
Yes.
Okay, good. So the last model is actually very, very simple. It says the following, guys. We're kind of missing, you know, within these models. You know, some models gives us good idea of this distribution. Other models give us good idea on, you know, on clustering. Can we actually sort of combine those things? This is very sort of, and the funny thing is, okay, this model created, this is the last model I'm going to talk about, is created by physicists. And so physicists like, you know, very, very abstract thinking. And they said, okay, well, let's look at this graph that is sort of connected in this loop. And the reason why you want loop is because you don't want boundaries, right? So like you're minimizing the number of boundaries, right? If you put it on the line, there'll be 2 endpoints, right? And if you put it in the loop, well, there is no endpoint. So that's just sort of, that's the only reason. I mean, you don't have to do it, you know, in a circle, in a circular way. But this is how originally it was done. And so the idea is very simple. Imagine this type of graph. And what's important about this graph is, you know, it all consists of triangles, right? There are a lot of triangles in here. And so this graph satisfies this idea of local dense connectivity. That the fact that locally, you know, your friends know each other. So that's sort of what we still couldn't reproduce in previous models. But this particular graph, of course, completely misses the distribution of node degrees, because, you know, all node degrees have the same degree here. All nodes have the same number of friends. But the second thing, what's missing is this, the notion of a small world. Because you're very densely connected locally, so you have a lot of connections locally. But in order to get from here to here, you'll have to make 1, 2, 3, 4, 5, 6, 7 steps. Now that's terrible for a graph that has like less than 100 nodes, right? So the diameter of this graph is very large. So you have 2 contradictory things. On one hand, you want to have locally a lot of connections, right? On the other hand, you want to have like long range connections. Think about this. Imagine that, you know, you spend all your time with your friends, like from high school friends or your university friends. Well, you don't have any time left for any other friends outside of university. So you still have to somehow balance this, right? You want to be able to have long distance, connections. And you want at the same time to have maybe some local connections, and the local connections give you triangulation because the friends within your group know each other. But long distance connections, you know, you probably have friends from your hometown, and you also have friends, I don't know, maybe you know somebody in Paris, right? And they most likely do not know each other. But that shortens your distance from you to anybody who's living in France, right? And that's pretty much the model. So what the guy said, oh, well, you know what? Screw it. We want a short distance and long distance at the same time. Well, let's do this. Let's just start with the model with short connections like we have here. And then let's just, you know, add some long distance connections. We can either just add them Or if we want to preserve the total number of connections, we can say, okay, well, let's just unlock this one and rewire, say, this into this, and just cut this and use this edge to connect somebody long distance. Now, it's clear that if you entirely reconnect it to long distance connections, you will have a small world, but you're going to lose your clustering. You're going to lose triangles. If you stay on the side of triangles, well, you don't have long distance. So somewhere in the between, you might still find this balancing point where you have enough triangles to have high clustering coefficient, and you still have like long range connections. All right, so that's sort of the goal. And that's what they, of course, did. Start with regular lattice with some number of edges per vertex, right? Some number of connections per vertex, and randomly connect with other nodes to form this long distance connections. And when you start at 0 long distance connections, you're on this regular graph story, like a lot of triangles. And when you go to all random connections, that's your random graph. We've been there, we already studied it at the beginning. And so what they showed is that, in fact, yes, you start, and by the way, P here doesn't mean the same as in the random graph. It's not the probability, it's probability of rewiring. It's just unfortunate collision of names. But if you start with regular graph where everything is connected locally, you have very high triangulations. If you go very much onto the right, you have completely random graph. But somewhere in between, they showed that there is a small world graph lives, where the graph still have triangles, enough triangles to have high clustering, but it's long distance, and so it's small world. And this is an example of this 20% rewiring. You take this type of a graph, which is locally connected, so there is a lot of triangles in here. And average path length in here is 358. It's just I calculated. And clustering coefficient is 0.5. And then I do 20% of those connections. I rewire them, at random. So now it looks like mess. But there is still some local connections preserved. And average path length drops because of the long distance connections. Clustering coefficient also drops because I destroyed some of the triangles. But overall, it's not completely destroyed. It's not as bad as in previous models. So this kind of preserves locality and gives you long-range relations. And it's called Watt-Strogatz model by the name of physicists who actually came up with this model. And going into this model, you can actually calculate things. It's not as clean and nice as previous models, but you can show that degree distribution will be Poisson-like. So the same way as in random graph. But the average, of course, path lengths will be logarithmic with number of nodes. So there is long range connections. And the clustering coefficient is fixed because we do have a lot of triangles. So this model is sort of done by construction. We wanted to construct long distance and preserve clustering. We did it. All right. Now you can say the nature doesn't work that way. I'm saying yes, it doesn't. But the model shows that, in fact, in reality, what we have is this combination of short distance stuff and long distance. And if we do, we can demonstrate that the model will have both small world properties and still large clustering coefficient, or this triangles. So looking through this whole thing of these models, these are the 3 models we studied: random graph, Barabasi-Albert, Watt-Strogatz. And these are the sort of the properties that they possess. And we notice that this, and I'll just write on top of the slide. We notice that empirical networks have power law degree distribution. Barabasi-Albert does have it. Random graph doesn't have it. Watt-Strogatz doesn't have it. Clustering coefficient in real networks is large. Watt-Strogatz does it. Barabasi-Albert does not. Random does not. And there is a small world. Well, all 3 of them have small world one way or another. And then there is a gigantic connected component, which I didn't show, that actually present in random graphs. So that's the story. These are 3 models. Pretty much since then, and as I mentioned, this model is like 1950, and this is like both 1999 or 2000. Of course, since then, there has been lots of new models published, but they're all usually use some different fragments or approximation of these ideas. So these models becoming like building blocks of the models that are much more much better reproduce the reality, right? And so to answer the question I have right now in the chat, so that again, back then those models were used like to reproduce the reality. Now they're all considered as a sort of teaching models to understand the properties, but the models that people try to sort of build to reproduce the real behavior, they usually consist of combination of this type of models, maybe some different parameters, and sometimes you use different models to describe different parts of networks, or different models to describe different parts of distribution. Sort of as you remember, we saw at the distribution there were like real life points were like that, and the model would use a straight line. So what you can say is, okay, you map the straight line here, and then you map something else in there. So models that work the best now, they're usually sort of ensemble models built from different blocks. All right, guys, that's pretty much it for today. Unfortunately, I cannot stay and take questions. Ilya Andreevich will try to answer all the questions you have. If there is still some questions remains, please email me, or we can discuss it next time. All right?
Yes, thank you.
All right, well, thank you very much. That's it for today.
So we'll start in 5 minutes. Those who are online listeners, let's switch a Zoom mass meeting. Thank you. So 5 minutes break, and we'll have maybe not so long.
Bye.
Bye.
Good day.